Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 1.2, Proof by Induction. Proof by induction is often seen as something quite difficult to do, but in a nutshell it's just rearranging and factorizing. In this video I'm gonna teach you two types. One is just do induction in general, and the second one is to prove divisibility, and I'm gonna tell you what that means in the example section. So proving induction in general is just simply you have an expression and you need to show that it equals to another expression for all integer n's that is in a certain range. Most of the time it would be greater than or equal to 1. Sometimes it can start from 0. And yeah, let's have a look in this one. So first of all, to do induction, you first start with the first value, which is k equals to 1. So the first value for k is 1 is 2 to the power 1, which gives us 2. And on the right we have a value 2 to the 1 plus 1 is 2 to the 2, take 2, which also gives us 2, because this is 4 take 2. And so we have shown that it is proved for k equals 1. So after we've done this, what we need to do is to say a hypothesis. Say that assume the sum to the n of k is 1 is of 2 to the power k is indeed 2 to the n plus 1 take 2. Then what we can do from this is we add an iteration which is up to n plus 1. And so for sum to n plus 1 from k equals 1 of 2 to the k will give us just this term plus the new term, which is also 2 to the n plus 1 take 2. That's the first term. Then we add the new term that we have added, which is 2 to the power of n plus 1. With that, we can simplify this expression to 2 lots of 2 to the n plus 1 add 2. And this value 2 times 2 to the n plus 1 is also 2 to the n plus 2. Don't forget the plus 2. And with that said, we can factorize out this n plus 2 into let's see, 2 to the n plus 1 in brackets plus 1 add 2. And guess what? This expression is the n plus 1 version of this expression. And whenever you do induction, make sure you definitely state it clear what is the n plus 1 value. So if you leave it as 2 to the n plus 2 plus 2, strictly speaking you have done it, but in order to get all the marks you need to display just be obvious what you're doing. And so if you put it in this form, then you should be able to just get everything that you would need in order to complete this set of questions. So this is the first induction example. Since it works for n as 1 or k as 1, we know from this result, you need to write this down by the way, just write down in words, since it works for n k equals 1, by induction it works for k equals to any n values that is greater than 1, then you should be able to complete the induction. If you don't write that sentence down and you just end it here, it's not gonna be sufficient. So let's go on for the next example where we prove for divisibility. So next up we have proof of this divisibility. This one is a bit more tricky than the straight induction, but in general it's still the same thing. So prove that 6 to the n plus 4 is divisible by 5 for n is greater than or equal to 1. So let's start with the value of 1. 6 to the 1, if I choose the correct pen, 6 to the power 1 plus 4 will give us a value of 10, which is indeed divisible. With that said, we can state that 6 to the n plus 4 is equal to 5k's, where k is an arbitrary number, and this is assume true. With that assumed, then we can try to add 1 to n, which is 6 to the power n plus 1, add 4 should be equal to 5 lots of, let's say, u, 5 lots of u, where u is a different value from k. And if we try to equate, it will be difficult, but it's doable. So we can express 6 to the n plus 1 as simply 6 lots of 6 to the power n equals to 5u. Then 6 to the n is just 5k take 4, which gives us 6 lots of 5k take 4. Add a 4 is 5 lots of u. From then, expand the bracket to get 30k take 60, 24, 64, that's not the right one. Add 4, give us 5u. And that's just simply rearranging and expanding everything. There's no logic to it really yet. Now cancel out the 4s from the just numbers. We should have a 5u take 20, 30k. And from that, we can definitely factorize out a 5 to get 6k take 4 equals to 5u. And thus, we have shown that it works for n plus 1 if n is true. And we know that n is true if n is 1. And therefore, this can be used to induce that, therefore, prove for or n greater than or equal to 1. And yeah, that's all there is to induction really. So when it comes to induction proofs, there isn't really much to say in terms of tips. The most important thing, I believe, is the ability to properly factorize things, and also algebra rearrangement will help a lot when you're doing it. But to be honest, the more trial question you've done, the more likely that you're going to be able to do it reliably, so do go and look for practice questions. Finally, the question section. I've given you 2 standard proofs that is in fact required for you to be able to do. So both of them uses the proof by induction, and one of them is the proof of the sum of integers, one of them is for the sum of the squares. I'm pretty sure you need to do sum to the cube as well, but all of these are on the MEI equation booklet, so you can look it up, just the general form, and do the induction proof if you have time. And once again, like chapter 1.1, there is no answer to proofs, so yeah, this will be the end of this video, and I hope you've learned something. And if you have any questions, do leave a comment in the comment section below, and I will see you on my next one.